The universe begins in silence. A silence so vast, so complete, it seems eternal. An endless ocean of nothing, smooth and still, without horizon or shore. But silence can be deceiving. Beneath the glassy surface of this void, something restless stirs. Physicists once believed emptiness to be truly empty, a hollow stage upon which matter and energy play their roles. But modern science has revealed a different truth. What appears as void is not absence, but presence of the strangest kind. Beneath the stillness, the vacuum, SEETH, ES. This is the quantum sea, a storm hidden beneath the fabric of existence. Invisible waves ripple through the void. Particles emerge from nothing, flicker into being, and dissolve again in less than an instant. Energy surges upward, vanishes, and returns, as though reality itself breathes in silence. It is a tempest that never rests, a storm that no eye can see. Every atom floats upon it. Every galaxy drifts above it. The stars themselves, burning across eternity, are anchored in turbulence older than light. The quiet storm of the quantum vacuum is not background, not scenery. It is the foundation, the bedrock of being. And yet, it is also a paradox. A nothing that is not nothing, a silence that roars in mathematics, a storm that holds within it the fate of the universe. From this hidden turbulence arose the seeds of galaxies, the birth of matter, the expansion of space. And perhaps, from it, will also come the end. If the deepest layer of reality is a storm, then what does it mean to say something exists? And could this invisible tempest one day rise from beneath its still ocean, consuming the universe it has always sustained? The idea of nothing has always haunted human thought. To imagine absence is to confront a mirror too dark to see through, a silence too deep to measure. Ancient minds stood beneath the night sky, gazing upward at its emptiness between stars, and wondered what lies in the spaces where there is no light. What fills the infinite gulf between worlds? In Greece, Aristotle declared that nature abhors a vacuum. To him, emptiness was impossible, a contradiction in terms. Space, he argued, must always be filled with some substance, some medium, however subtle. For centuries, this conviction shaped the philosophy of science, that the universe was whole, continuous, without void, and yet others disagreed. Democritus, imagining atoms as the indivisible bricks of matter, insisted that between them lay the void, an infinite emptiness, without which motion would be impossible. Two visions of reality, one of fullness, one of emptiness, wrestled for primacy in the human mind. For millennia, emptiness remained a philosophical puzzle rather than a scientific one. The skies were mapped, planets traced across the heavens, comets charted in their sweeping arcs. None of these demanded a deeper reckoning with the nature of the void. The stars burned against a backdrop assumed to be passive, silent, and still. It was Isaac Newton who first gave emptiness a kind of authority. In the 17th century, his laws of motion and universal gravitation were cast upon the canvas of absolute space, a stage, vast and immutable, on which the planets circled the sun in endless measure. Space itself was the container, time the eternal clock, both indifferent to the drama within them. Newton's cosmos was vast, cold, and still. Emptiness was real, but inert. Yet even here, doubt persisted. If light was a wave, what medium did it travel through? In the 19th century, physicists proposed the luminiferous ether, a a ghostly substance that filled all of space, invisible and intangible, but carrying the vibrations of light across the void. For decades, it was taken as fact. Light must ride upon something, for how could a wave exist without a sea to ripple? The ether was tested, searched for, hunted. In 1887, Albert Michelson and Edward Morley built one of the most delicate instruments of their age. Their interferometer sought to measure Earth's motion through this invisible medium, but the result was nothing. No drift, no shift, no sign of the ether. Light required no ocean to sail upon. The void, it seemed, was empty after all. It was. Albert Einstein, who drove the final nail into the coffin of the ether. In 1905, with his special theory of relativity, he declared that light needs no medium. Space and time themselves were enough. In their union lay the geometry of motion, and in that geometry no hidden ether was required. For a moment, emptiness returned to silence, the stage stripped bare once more, but silence would not last. The 20th century saw the birth of the quantum revolution, and with it the unraveling of every certainty. Max Planck, seeking to explain the spectrum of black-body radiation, introduced the idea that energy comes in discrete packets, quanta, soon. Werner Heisenberg unveiled the uncertainty principle, that particles could never be pinned down with absolute precision. At the smaller scales, nature was restless, unpredictable, alive with flicker and flux. This restlessness carried a shocking implication. If particles could never be perfectly still, then even in their absence, fluctuations must remain. Emptiness could not be truly empty. Paul Dirac, in the 1920s, went further still. His equations, blending quantum mechanics with relativity, described a universe in which particles of negative energy filled the vacuum like an invisible ocean, the deep sea. From its depths, a prediction surfaced. Antimatter, a mirror to the particles we know, born from the mathematics of a storm hidden in the void. In time, this storm revealed itself not just in equations, but in experiments. The Lamb shift, measured in 1947, showed that the energy levels of hydrogen atoms were subtly altered by the flicker of quantum fluctuations. The Casimir effect, discovered soon after, revealed that two uncharged metal plates placed close together would be pushed inward, not by any visible force, but by the pressure of the vacuum itself. The void had weight, pressure, and consequence. What philosophers had once called nothing was becoming something tangible, not a silence, but a sea, not emptiness, but storm. At the scale of the cosmos, the same truth was written even larger. In 1965, Arno Penzias and Robert Wilson tuned their radio antenna and stumbled upon a faint, pervasive hiss. It came from every direction, constant and unrelenting. This was the cosmic microwave background, the fossil light of the Big Bang. Itself stretched thin across the expanding universe. Within that light were fluctuations, faint ripples in temperature, only 1 part in 100,000. These tiny variations carried the fingerprints of quantum fluctuations magnified by cosmic inflation. From the storm in the vacuum arose the seeds of galaxies, the scaffolding of the cosmos. The great structures of today, spiraling galaxies, clusters and filaments stretching across billions of light years, were once whispers in the quantum sea. The void, it turned out, was the author of form. By the end of the 20th century, the picture had become undeniable. What had once been seen as nothingness was, in truth, a restless foundation of reality. Quantum electrodynamics described the vacuum as alive with virtual particles, constantly appearing and disappearing, obeying the uncertainty principle's relentless demand for motion. In the mathematics of the quantum fields, the vacuum was not absence but presence, a lowest energy state, seething with potential. Every experiment confirmed it. The shifts in atomic energy, the pressure between plates, the scattering of light by the flicker of the void. Each result whispered the same truth. Emptiness is storm. Yet this storm was not merely a curiosity of the small. It shaped the universe itself. The inflationary epoch, less than a fraction of a second after the Big Bang, was driven by the energy of the vacuum, an expansion so rapid it smoothed the cosmos and planted the seeds of all structure to come. The faint hiss of the CMB was its lingering echo, a memory of a storm older than stars. And so, the discovery phase ended in awe. Humanity had stared into nothing and found it filled with everything. The void was no longer passive background, no longer a silent stage. It was actor, author, and architect. The quiet storm beneath the quantum sea had been revealed, not by myth, not by speculation, but by measurement, by mathematics, by the stubborn insistence of reality itself. But with this discovery came unease. For if emptiness is storm, what becomes of stability? If the ground of being is restless, what holds reality steady? What science had uncovered was not only a foundation but a paradox, a silence that roared beneath the skin of existence, a storm, invisible yet irresistible. And behind that paradox lay questions even darker, even deeper, waiting to break. The discovery that the vacuum is not empty was not merely a scientific correction. It was a rupture, a collapse of one of humanity's deepest assumptions. For millennia, the void had been thought of as absence, silence, a neutral canvas on which matter and energy painted their fleeting forms. To reveal, instead, that the void itself is alive, restless, seething with invisible energy, was to discover that the ground beneath existence is storm rather than stillness. At first, this revelation was subtle, a shift in the frequencies of hydrogen, an inexplicable pressure between polished plates of metal. Tiny discrepancies only the most delicate instruments could see. But in their shadows lay something colossal. These were not anomalies. They were messages. They spoke of a universe in which nothingness was not nothing at all. The shock deepened when scientists turned the equations of quantum field theory toward the cosmos. In their mathematics, each field, electromagnetic, nuclear, Higgs contributed a baseline energy even in its lowest state. This zero-point energy, when summed across the quantum sea, grew vast, unimaginably vast. The result was staggering. Quantum theory predicted that the vacuum should be filled with energy 10 times greater than anything astronomers observed. This was not a small error, not a refinement waiting in the margins. It was the greatest mismatch in the history of science, the cosmological constant problem. If quantum physics was correct, the fabric of space should be torn apart by its own energy, exploding in violent expansion long before galaxies could form, long before stars could ignite. And yet the night sky was calm. The galaxies spun. The earth endured. Reality existed. How could this be? It was as though two mirrors reflected contradictory truths. Mathematics showed a storm so violent it should annihilate all form. But the universe displayed a silence gentle enough to harbor life. Somewhere between theory and observation lay an abyss of ignorance. The paradox only, sharpened when black holes entered the stage. At the edge of their horizons, where gravity bends time itself, The quantum vacuum flickers with strange intensity. Stephen Hawking, in 1974, revealed that black holes are not truly black. They glow. Virtual particles born from vacuum fluctuations near the horizon can become real, one escaping into the cosmos while the other falls within. This trickle of radiation, Hawking radiation, means black holes evaporate. The implication was profound. The void can create heat. Nothingness can radiate. The most empty reaches of space possess the potential to burn. For the scientific world, this was an earthquake. If the vacuum can destroy black holes, if it can fuel the birth of galaxies, if its predicted energy dwarfs everything else, then the void is no background. It is the dominant actor in the cosmic drama. The stars, the galaxies, even life itself may be nothing more than ripples upon its restless surface. And yet, this actor remains invisible. Physicists described the vacuum as filled with virtual particles, flickering into and out of existence. But these ghosts cannot be observed directly. They appear only in their effects, the shift of spectral lines, the pressure in experiments, the subtle forces shaping atoms and stars alike. We see only their fingerprints, never their faces. This invisibility gnawed at the human mind. How can something so powerful, so central to existence, remain forever beyond direct perception? And if the vacuum is unstable, if our universe is only a false vacuum, perched in a temporary state of energy, then existence itself is fragile. Here lay the most haunting possibility. The storm beneath the quantum sea might one day rise. A single fluctuation, a single quantum spark, could collapse the false vacuum into a deeper state of energy. The laws of physics would be rewritten in an instant. Protons, neutrons, atoms, stars, all would dissolve as the new vacuum swept outward at the speed of light. No warning, no escape. The universe, steady in appearance, was revealed to be balanced on a knee. Its ground state was not ground at all, but a ledge above an abyss. This was the scientific shock. Not simply that the vacuum is restless, but that it is paradoxical. Its energy is both infinite and almost nothing. It destroys and creates, erases and sustains. It burns black holes to ash while birthing galaxies from whisper. It contains the potential for eternity and the seed of instant annihilation. Physicists struggled. Equations clashed. Relativity declared that energy curves space, that the vacuum should sculpt the destiny of the cosmos. Quantum theory insisted that fluctuations are real, measurable, undeniable. But when these truths were combined, contradiction erupted. The storm refused to be tamed by mathematics. The human imagination reeled. To live in such a universe was to accept that nothing was the most mysterious something of all. Every breath, every heartbeat, every flicker of starlight, balanced upon a storm invisible to the eye, immeasurable by direct means, unknowable in its true depth. The void had betrayed its silence, and with that betrayal came fear. If nothingness is unstable, then all of existence may be temporary. If the vacuum is filled with infinite energy, then all of existence may be fragile. If the quantum sea is the real foundation, then we are children of turbulence, not of order. It was here, in the late 20th century, that physics felt its foundations tremble. Scientists had uncovered the quiet storm beneath the quantum sea, and discovered that its implications were stranger, more terrifying, and more beautiful than anything myth had imagined. The shock was not in the discovery that emptiness is storm. The shock was in realizing that all of reality may be written in its waves. The revelation that the vacuum was not empty did not end the story. It only deepened the enigma. For science, the next step was not to recoil in shock, but to measure, to test, to reach with instruments into the silence and draw out its hidden storm. If nothingness carried structure, then perhaps its fingerprints could be found not only in equations, but in experiment. The first evidence came in whispers. In 1947, Willis Lamb and Robert Rutherford probed the hydrogen atom with radio waves, expecting the electron's orbit to conform precisely to Dirac's predictions. Instead, they found a subtle shift, a displacement so tiny it seemed almost absurd. Yet this Lamb shift could only be explained if the vacuum itself was pressing upon the atom, fluctuating with invisible energy, tugging at the electron's dance. In the laboratory, emptiness had spoken. Soon after came the Casimir effect. Hendrik Casimir predicted that two parallel metal plates, placed nanometers apart, should feel a pressure, not from any force between them, but from the absence of modes of the quantum vacuum between their surfaces. When tested, the plates moved. They slid toward one another, pushed by nothing at all. The void had weight, pressure, a hand that could move matter to some. These were technical results, refinements in the machinery of physics. To others, they were revelations. They proved that empty space was not passive, but active, a sea whose invisible waves could shape the tangible. Humanity had begun to measure the storm, but the vacuum's role was far larger than the laboratory. Cosmology carried the investigation into the sky. In 1965, Arno Penzias and Robert Wilson tuned their radio antenna in New Jersey, attempting to remove a faint hiss of noise. The hiss refused to vanish. What they had discovered was the cosmic microwave background, the relic radiation of the Big Bang. Embedded in its faint glow were fluctuations, minute variations in temperature and density, whispers of quantum fluctuations magnified by inflation. Here lay one of the greatest surprises: the galaxies. Clusters and vast filaments of the universe were seeded by storms in the vacuum itself. The ripples of nothing had become the architecture of everything. The largest structures in the cosmos were born not from stars, not from matter, but from tremors in emptiness, amplified across the expanding sea of spacetime. Satellites sharpened the view. COBE in 1989 confirmed the CMB's uniform glow. WMAP in 2001 and Planck in 2009 mapped its fluctuations in exquisite detail, revealing patterns across the sky with precision down to millionths of a degree. These maps showed the storm's ancient face. The vacuum had sculpted the universe, and yet, the deeper the investigation, the stranger the results. Particle physics revealed that the vacuum was not uniform. It was filled with fields: electromagnetic, weak, strong, Higgs. Each field carried potential energy. The Higgs field, discovered in 2012 at CERN, was not simply a particle but a property of the vacuum itself, an invisible sea that gives mass to all fundamental particles. Without this background, electrons would remain weightless, atoms could not form, stars could not shine. The vacuum was not absence. It was the very medium in which reality took shape. But if the vacuum was so essential, then why did it appear so finely balanced? Quantum electrodynamics, QED, required its fluctuations to explain atomic behavior. Quantum chromodynamics, QCD, suggested that the vacuum was filled with virtual quark-antiquark pairs, shaping nuclear forces. And yet, when all contributions were summed, The calculated energy density exceeded the observed value by 120 orders of magnitude. This was not merely an error of measurement. It was the most profound rift in physics. The storm beneath the quantum sea appeared infinite in theory, yet almost negligible in practice. Why? Scientists probed further. High-precision experiments measured the Casimir force with increasing accuracy, confirming vacuum pressure down to nanometer scales. Spectroscopy refined the Lamb shift. Quantum optics revealed squeezed vacuum states, where the fluctuations could be manipulated, reduced in one property while amplified in another. The storm was not random chaos, but a pattern that could be tuned. COSMOLOGISTS searched the sky. Baryon acoustic oscillations, imprinted as ripples in the large-scale distribution of galaxies, offered further evidence. These ripples were fossil sound waves, born of fluctuations in the early plasma, amplified by the vacuum during inflation. The cosmic web itself, a lattice of galaxies and voids, was the memory of quantum tremors billions of years old. Meanwhile, physicists turned to the most extreme objects in the universe, black holes. Hawking's theory suggested that the vacuum at their horizons produced radiation. Observatories searched for indirect evidence of this evaporation, though none yet has been seen. But black holes offered more than theory. They were laboratories where gravity and quantum fluctuations collided. Near their edges, the vacuum became turbulent, perhaps offering a key to uniting relativity and quantum theory. The investigation widened into new territory. Neutrino oscillations hinted at vacuum contributions, while dark matter searches revealed anomalies that could be tied to vacuum fields. In particle accelerators, researchers probed whether the Higgs vacuum was truly stable. Measurements suggested it might be metastable, perched precariously with a possibility of collapse into a lower energy state. The false vacuum was no longer abstract speculation. It was a hypothesis with data. Each layer of investigation revealed a deeper paradox. The vacuum was measurable, yet untouchable. It was essential, yet contradictory. It shaped galaxies, yet threatened annihilation. The more instruments revealed, the less solid reality appeared in this growing web of discovery. One theme repeated: the vacuum is not one thing. It is layered, complex, perhaps even multiple. String theory spoke of a landscape of vacua, minus 10,500 possible versions, each with its own laws of physics, each a different storm. Our universe might simply inhabit one among many, chosen by chance or necessity. The quiet storm beneath our quantum sea might not be unique, but one eddy in an infinite multiverse, and still. The investigation pressed forward. Gravitational wave astronomy, in its infancy, hinted at a new probe. LIGO's detection of merging black holes in 2015 opened a channel to listen for spacetime tremors. Could primordial gravitational waves, born from inflationary vacuum fluctuations, be detected in the polarization of the CMB? If so, humanity would hear the echo of the quantum storm at the dawn of time. The search continues. Laboratories press metal plates ever closer. Telescopes scan the CMB with sharper eyes. Colliders probe the Higgs with finer resolution. Pulsar arrays listen for the deep bass of gravitational symphonies. And all the while, the question grows louder. What is the vacuum? Is it a storm of virtual particles, a sea of fields, a holographic code on the boundary of space-time, or something even stranger? The deeper the investigation, the less certain the answer. But one truth shines clear. The The vacuum is not absence. It is the foundation, restless and alive. Everything, galaxies, stars, atoms, minds, emerges as a fleeting form upon its surface. The storm remains quiet, invisible, but it is there, beneath the quantum sea, shaping everything we see, everything we are. The deeper science looked into the vacuum, the more unsettling the storm became. What had first appeared as a subtle correction in atomic spectra had now swelled into a cosmic force, one that shaped the entire universe and perhaps even threatened its survival. The storm beneath the quantum sea was not simply a background hum. It was the dominant presence in the cosmos, quiet yet absolute. In 1998, two teams observing distant Type Ia supernova discovered that the universe's expansion was accelerating. This was not supposed to happen. Gravity, the great binder, should have been slowing the cosmic drift, tugging galaxies gently inward even as space expanded. Instead, the galaxies receded faster, as though some hidden hand were pushing them apart. That hand was given a name, dark energy. But dark energy was not another substance, not some invisible fluid drifting between galaxies. The simplest explanation was that it was the energy of the vacuum itself, the very storm predicted by quantum theory. The quiet sea beneath everything was not only shaping atoms, it was inflating space. The storm had become the ruler of the cosmos. This realization brought with it the greatest paradox in physics. The measured value of dark energy was incredibly small, enough to accelerate the universe, but only gently, producing doubling times of tens of billions of years. Yet quantum field theory predicted that the vacuum's energy should be catastrophically large, enough to tear spacetime apart instantly. Between theory and observation lay a gulf of 120 orders of magnitude, the largest discrepancy in all of science. This is known as the cosmological constant problem, and it is not just an error. It is a mirror reflecting something profoundly broken in our understanding of reality. The mystery deepened further when physicists realized that the universe might not be stable at all. The discovery of the Higgs boson at CERN in 2012 confirmed the existence of the Higgs field, an invisible ocean giving mass to particles. But measurements of the Higgs mass and its coupling to other particles suggested an unsettling possibility. Our universe's vacuum state may not be the lowest energy configuration. Instead, it may be a false vacuum, precariously balanced in a valley of stability, but with a deeper valley lying beyond. If a quantum fluctuation ever nudged a region of space into that lower valley, a bubble of true vacuum could form, expanding at the speed of light and rewriting the laws of physics in its wake. This would not be an explosion in space. It would be an explosion of space itself. Every particle, every atom, every structure would be annihilated as the new vacuum erased the old. The storm beneath the quantum sea would rise, not in silence but in finality. Physicists live with this possibility as a mathematical truth, and yet they know it cannot be predicted. No detector can warn of vacuum decay. If it happens instantly, everywhere, without sound, without light. A silent end, born from the instability of nothing itself. But even this terror is only one branch of the storm. Some models of inflation suggest that the early universe itself was seeded by vacuum fluctuations, that a field, the inflaton, dominated space, driving an exponential expansion. This expansion smoothed the cosmos, but it may never have fully ended. In the inflationary picture, our universe may be one bubble among many, each region inflating and branching, each with its own vacuum, its own physics. The storm may not be local. It may be infinite, cascading across amultiverse. Here, the quiet storm grows louder. If every possible vacuum exists, if every possible law of physics unfolds in some corner of the multiverse, then what is the meaning of ours? Is our vacuum's delicate balance, its near instability, its gentle acceleration, merely a random draw from a vast cosmic lottery? Or is there some deeper principle that guided the storm to settle here in this precise form, with laws finely tuned to allow galaxies, stars, and life? Observations only deepen the puzzle. The cosmic microwave. Background reveals subtle anomalies. The cold spot, a region cooler than models predict, and strange alignments known as the axis of evil. These features may be statistical flukes, or they may be imprints of primordial vacuum fluctuations, scars left by collisions with other bubble universes, traces of a storm far beyond our cosmic horizon, even within our own galaxy. The vacuum storm shows itself in unexpected ways. Pulsars, rotating neutron stars. The densest remnants of stellar collapse sometimes glitch, suddenly shifting their rotational period. Some theorists suggest that these glitches may be tied to vacuum processes deep within their cores, where quark, matter, and vacuum fluctuations intertwine. If so, then the storm is not distant. It shakes the densest hearts of stars. Black holes add another layer of mystery. At their event horizons, the vacuum seethes. Hawking radiation, born from vacuum fluctuations at the edge of no return, suggests that black holes evaporate over time. Yet this clashes with relativity, which sees event horizons as eternal. The result is the black hole information paradox. Does the vacuum erase information, or does it preserve it in ways we do not yet understand? If the vacuum is the stage upon which reality plays, then perhaps it also keeps the script, encoded not in particles but in correlations, entanglements spread across horizons. In some theories, spacetime itself is woven from entanglement within the quantum vacuum, a storm of information whose patterns generate geometry itself. The quiet storm is not beneath spacetime. It may be spacetime. All the while, the accelerating expansion grows stronger. Distant galaxies recede faster than light, slipping beyond our cosmic horizon. The universe becomes lonelier with each passing epoch. 1 trillion years from now, observers in distant galaxies will see only their own island of stars. The rest of the cosmos will be gone, erased not by destruction, but by distance, hidden behind horizons drawn by dark energy. This too is the storm at work. The quantum vacuum dictates not only the smallest scales, but the largest, the fate of time, the end of visibility. The storm beneath the quantum sea is erasing the sky itself. Philosophers once spoke of the void as terrifying because it was empty. Today, it terrifies because it is full of energy, instability, and hidden rules we cannot decipher. It is the most dominant force in the cosmos, and yet the least understood. It seeds galaxies, bends atoms, drives expansion, threatens destruction, and through it all, it remains invisible. A storm without sound, a pressure without surface. The mystery has only escalated. What was once the quiet background has become the main actor. The vacuum is not silence. It is power, order, chaos, and perhaps destiny. The storm beneath the quantum sea has risen from theory into inevitability. And still, the question deepens. Is this storm a feature of reality, or the foundation of it? Does it emerge from spacetime, or does spacetime emerge from it? The more science uncovers, the more it seems that everything we call something is simply a ripple in this hidden ocean, and the storm remains, always unseen, always beneath, always waiting. When the known laws of physics strain under the weight of paradox, speculation is no longer indulgence, it becomes necessity. The storm beneath the quantum sea forces science into this realm, where mathematics extends beyond experiment, where thought experiments become lanterns carried into darkness. The first and most powerful speculation is that of inflation. In the early universe, something extraordinary happened. Space itself expanded faster than light, smoothing chaos into uniformity and seeding structure with delicate ripples. What drove this? Physicists speak of the inflaton field, a quantum field whose vacuum energy was so immense that it overwhelmed gravity. For a fraction of a second, the universe ballooned, expanding by factors beyond imagination. Then, as the field decayed, energy poured into particles, into light, into matter. Galaxies would one day grow from the tiny fluctuations left behind. Inflation is more than a theory of beginnings. It suggests that the vacuum itself is the engine of creation, that the storm is not a consequence but the cause. Yet inflation carries with it a dangerous implication. If the inflaton field could drive one universe, why not many? Most versions of inflation predict that it never ends everywhere at once. Some regions decay into universes like ours, while others continue inflating endlessly. This is the concept of eternal inflation, a multiverse birthed not from speculative philosophy, but from the logic of vacuum fields. In such a picture, our universe is one bubble in a storm without boundaries. Our laws of physics, one dialect in an infinite chorus. From here, the storm grows even more complex. String theory, the leading candidate for a theory uniting quantum mechanics and gravity, does not describe one universe, but a landscape of vacua, perhaps 10,500 possibilities, each with its own constants, its own symmetries, its own storm. In this landscape, the vacuum is not unique. It is a vast terrain, and our universe's peculiar balance may be nothing more than a valley among countless valleys. Why does our universe accelerate with precisely this strength? Perhaps because only such a vacuum permits galaxies, stars, chemistry, and observers. This reasoning is known as the anthropic principle, unsettling, but difficult to avoid in a storm that contains infinities. Other theories attempt to stabilize the storm by adding new symmetries. Supersymmetry predicts that every known particle has a hidden partner, a shadow twin. If true, vacuum energy contributions from particles and their partners would cancel, taming the storm. But as experiments at the Large Hadron Collider search for these partners, silence remains. Supersymmetry may exist at scales beyond our reach, or it may not exist at all, leaving the storm unbalanced. Meanwhile, the holographic principle offers a radically different speculation, proposed by Gerard T. Hooft and expanded by Leonard Susskind. It suggests that everything within a region of space can be described by information encoded on its boundary. In this view, the vacuum fluctuations inside the universe may be shadows of patterns written on the cosmic horizon. The storm beneath the quantum sea may not be beneath at all. It may be a projection, the illusion of depth cast by information inscribed elsewhere. Other thinkers approach from the side of gravity itself. Eric Verlin's emergent gravity argues that space-time and gravity are not fundamental, but emergent properties of quantum information, much as temperature emerges from molecules in motion. If this is true, then vacuum energy is not a correction to reality. It is reality. The storm is not a hidden force within spacetime. It is the knitting of spacetime itself. Yet speculation reaches its most haunting edge with the idea of false vacuum decay. If our universe is indeed perched precariously in a metastable state, then its future is a question not of if, but when. One quantum fluctuation, one tunneling event, could initiate a bubble of lower energy vacuum. Expanding at the speed of light, this bubble would not merely destroy matter. It would erase the very laws of physics, rewriting charge, mass, even dimension. In a sense, this would not be an end, but a replacement. Our reality swapped for another, foreign storm. The mathematics is clear. It could happen in the next instant, or not for trillions of years. Probability offers no comfort when certainty is absolute. But others dream of cycles instead of finalities. Loop quantum cosmology, derived from loop quantum gravity, suggests that singularities may be illusions. When densities grow extreme, quantum geometry resists collapse, creating a rebound, a big bounce. In such models, each universe ends in collapse, only to re-emerge as a new cosmos, seeded again by vacuum fluctuations. The storm does not end existence. It recycles it endlessly. Roger Penrose has proposed his own cyclic vision, conformal cyclic cosmology. In this framework, the remote future of a universe, emptied of particles and structure, becomes indistinguishable from the hot, dense beginning of a new cosmos. Black holes evaporating through Hawking radiation in one eon seed the fluctuations of the next. The storm beneath the quantum sea becomes not only an origin but an inheritance, passing its rhythm from one cosmos to another. Speculation even stretches to the metaphysical. Some argue that if vacuum fluctuations can generate particles, then perhaps consciousness itself is tied to these patterns, entangled with the storm. Though not mainstream science, such musings reflect a philosophical truth. If the foundation of reality is unstable, restless, forever seething, then nothing, not matter, not time, not even thought is independent of its churn. Yet amid these speculations, one fact remains constant. Without the storm, nothing exists. Inflation, multiverse, holography, false vacuum decay, cyclic cosmologies, all these models differ in detail, but each begins with the same premise. The quantum vacuum is not absence, but presence. It is not silence, but music without melody, a rhythm without beat. It is the most fertile emptiness imaginable, and in this lies the deepest philosophical speculation of all. If the storm beneath the quantum sea is universal, then perhaps existence is not defined by stability, but by restlessness. Perhaps reality is not a fortress of order, but a wave balanced on turbulence. To live, to think, to observe, is to ride the storm. The theories multiply, the speculations expand, but the mystery only deepens. The storm has no single explanation. It is a mirror, reflecting the boundaries of physics and the imagination of humanity. Whether it seeds multiverses, collapses reality, or encodes spacetime itself, it is the same storm, quiet, invisible, relentless. And so the question grows more profound. The storm may not be a feature within the universe. It may be the universe. Science does not confront mystery with silence. It confronts it with instruments, fragile extensions of human senses, built to capture whispers from the void, to understand the storm beneath the quantum sea. Humanity has deployed tools across every frontier, buried beneath mountains, orbiting in the cold dark, stretched across deserts, or suspended on threads of light itself. Each is a net cast into nothingness, hoping to draw up fragments of the unseen. The Large Hadron Collider near Geneva is one such net, the most powerful machine ever constructed by human hands. Protons are hurled to near the speed of light, their collisions creating fireballs reminiscent of the universe's first trillionth of a second. The LHC is more than a particle smasher. It is a test of the vacuum itself. When, in 2012, it revealed the Higgs boson, it was not merely the discovery of a particle, but of a field that pervades the void. The Higgs vacuum endows mass, stabilizes matter, and may yet determine the fate of the cosmos. By measuring the Higgs with exquisite precision, scientists now ask, is our vacuum stable or precarious? The storm's very foundations are under inspection, but colliders are only one path. In quiet laboratories, far from the noise of accelerators, researchers study subtler signatures of the vacuum. Two metal plates, placed nanometers apart in a perfect vacuum, are drawn together by an invisible pressure. This is the Casimir effect, a tangible manifestation of vacuum fluctuations. Sensitive instruments measure the force with increasing accuracy, searching for deviations that could hint at hidden fields or extra dimensions. Even in silence, the storm exerts a pull. Atomic physics provides another window. The Lamb shift, a tiny alteration in hydrogen's spectral lines, emerges only when vacuum fluctuations are included in theory. Precision spectroscopy, using lasers tuned to unimaginable sharpness, now measures these effects 2 parts per trillion. Each discrepancy, each unexplained deviation, is a possible ripple in the storm. Yet the vacuum is not only a laboratory phenomenon, it is a cosmic one. The discovery of dark energy in 1998 revealed that the expansion of the universe is accelerating, as though space itself is suffused with a pressure. If this is vacuum energy, then the storm is not a background, it is the dominant feature of the cosmos. To probe it, humanity builds vast surveys. The Euclid mission, launched by the European Space Agency, maps billions of galaxies, charting their distortions by dark energy across cosmic time. The Vera Rubin Observatory will soon scan the sky night after night, tracing subtle shifts in brightness and position, assembling a cosmic movie of the storm's effect. And above Earth, the James Webb Space Telescope peers deeper into time than any instrument before it. By studying the earliest galaxies, Webb seeks the fingerprints of inflation, the storm's first outburst. If primordial vacuum energy sculpted the infant cosmos, its echoes should remain in the arrangement of stars and dust at the dawn of galaxies. Each image, each red-shifted smudge of ancient light, is a clue to the storm's origin. The cosmic microwave background itself remains one of the most direct windows into the vacuum. The Planck satellite mapped its fluctuations with astonishing precision, revealing tiny variations in temperature across the sky. But the next generation, LIGHT-BR in Japan and CMBS-4 in the United States, will go further. They will search for the polarization patterns that inflation's vacuum fluctuations should have left. If found, they would confirm that the storm beneath the quantum sea did not merely whisper, it thundered creation into existence. Gravitational wave astronomy now adds another sense. The detectors, LIGO and Virgo, have already caught spacetime rippling as black holes collide. But their successors, the Laser Interferometer Space Antenna LISA, floating millions of kilometers apart in space, and pulsar timing arrays stretching across the galaxy, will search for waves from the very early universe. These ripples may be relics of the vacuum's first turbulence, the storm's deep bass notes. A detection would be nothing less than hearing the heartbeat of creation. Meanwhile, experiments at the smallest scales mimic the storm with quantum simulators. In ultra-cold laboratories, atoms are cooled to near absolute zero, arranged in lattice, and manipulated with lasers. These systems can recreate the mathematics of quantum fields, allowing physicists to watch vacuum-like fluctuations in controlled settings. In these artificial seas, the storm can be studied up close, providing analogues to processes otherwise hidden by cosmic distance. Other tools dig deep into the earth, shielded by rock, to listen for whispers of dark matter, another possible manifestation of the vacuum's unseen hand. Detectors like Xenon in Italy or Luxeplin in the United States watch for faint interactions in tanks of liquid xenon. Though results remain elusive, the search continues, for dark matter and dark energy may be intertwined storms, different facets of the same turbulent sea, even neutrinos, ghostly particles that slip through. Planets, as though they were air, serve as messengers of the vacuum. Their tiny masses may be linked to fields that hover just above the void. Observatories buried in Antarctic ice, such as Ice Cube, listen for their faint flashes, each a possible clue to hidden symmetries beneath the quantum sea. Supercomputers, too, act as instruments, simulating quantum fields across lattice of spacetime, generating predictions that experiments can test. The vacuum structure in quantum chromodynamics, the field that binds quarks into protons, is so complex that only computation can probe it. These calculations reveal a storm layered with vortices and instansons, topological twists in the vacuum fabric. Such features may leave imprints on cosmology, or explain why matter dominates over antimatter. All these tools, telescopes, colliders, detectors, simulators, converge on a single pursuit: to measure the unmeasurable, to capture the storm hidden beneath silence. And yet, despite decades of effort, the mystery persists. Each advance sharpens the paradox. The vacuum's fluctuations are real, but their energy remains inexplicably faint compared to theory. Dark energy is observed, but its nature remains opaque. Inflation is compelling, but unproven. The Higgs has been found, but its stability is uncertain. The storm will not yield easily. Still, humanity listens. From the deserts of Chile to the ice of Antarctica, from particle beams in Switzerland to satellites in orbit, a symphony of instruments is tuned to nothingness. Each waits for a discord, a ripple, a shimmer in the void. The quiet storm beneath the quantum sea is the most elusive of mysteries, but it is also the most fundamental. For to understand it is not only to understand particles or galaxies, it is to understand why anything exists at all. The story of the quantum sea does not end with equations or experiments. It ends in silence and in wonder. Beneath everything we see, everything we know, lies a storm so subtle it cannot be heard, yet so powerful it has shaped the cosmos itself. The quantum vacuum is not emptiness. It is not absence. It is not silence. It is the most crowded nothing imaginable, a perpetual churning of fields and fluctuations. Particles emerge, vanish, and emerge again, flickering like fireflies in a midnight forest. What we call reality rests not on solid ground, but on this restless turbulence, this invisible ocean beneath existence. Every galaxy, every star, every breath rises from its waves. The human mind has long sought stillness as a foundation. Philosophers imagined eternal forms. Physicists once imagined space as a static void. But science has revealed that at the deepest layer, stillness is an illusion. The cosmos is anchored in motion, in storm, in fluctuation. The void is not quiet. It trembles with hidden life. This realization is both terrifying and profound. Terrifying because it suggests fragility. If our vacuum is metastable, as some theories whisper, then one fluctuation could be enough to unravel the entire fabric of reality. In an instant, the storm could shift. The laws of physics, the very structure of matter, could dissolve, replaced by something alien. The universe would not end in fire or ice, but in transformation, sudden, silent, absolute. And yet, it is profound, because without this storm, nothing would exist at all. It was the vacuum's fluctuations that seeded galaxies in the early universe, that sculpted the cosmic web, that allowed stars to form and planets to coalesce. Without the storm, there would be no structure, no order, no life. Fragility and creation are intertwined. Destruction and birth are the same motion of the sea. Human beings, fragile themselves, exist in resonance with this truth. Every heartbeat is a fluctuation, every thought a pattern rising briefly from neural storms. Our lives are temporary ripples, emerging from silence and returning to it, just as galaxies emerge from the quantum sea and eventually dissolve back into it. To exist is to be momentary. To exist is to be stormed. There is a paradox here, the same paradox that lies at the heart of physics. On one hand, the universe is ruled by entropy, by the tendency toward disorder, by the slow fading into heat death. On the other, the storm beneath the quantum sea generates order, structure, patterns that persist against chaos. Out of the fluctuations of nothingness came galaxies, came stars, came consciousness. Out of instability came meaning. Perhaps then, the storm is not a threat, but a gift. Perhaps fragility is the condition for beauty. A universe without turbulence would be empty, sterile, silent. A universe built upon storm is alive, resonant, creative. Scientists continue to search for the storm's final truth. Is it stable? Is it temporary? Does it connect to hidden dimensions, or to universes beyond our own? The answers remain elusive, but even in uncertainty, there is clarity. The storm reminds us that existence itself is not guaranteed. It is contingent, fragile, precarious, and therefore infinitely precious in black holes. The storm is amplified, transforming vacuum fluctuations into Hawking radiation, hinting that even darkness glows faintly with the energy of nothingness. In cosmic expansion, the storm manifests as dark energy, propelling galaxies apart with invisible force. In laboratories, the storm pulls metal plates together, shifts atomic lines, alters charges. It is everywhere, and yet it is never seen directly. The storm is both the most universal and the most hidden aspect of reality, and so, humanity stands at the edge of a question not only scientific but philosophical. What does it mean to live in a universe where nothing is not nothing? If the void is alive, then reality itself is woven from uncertainty. If silence is storm, then existence is more fragile, more temporary, more miraculous than we can imagine. The implications stretch beyond physics. They touch meaning, identity, and destiny. If the vacuum is unstable, then permanence is an illusion. No structure endures forever. Not stars, not galaxies, not laws of physics. To live is to dwell in impermanence. But if the vacuum is fertile, if its fluctuations will always seed new patterns, then perhaps endings are not final. Perhaps every collapse carries within it the whisper of rebirth. Philosophers have long sought absolutes. Science has revealed storms instead. But storms, too, have beauty. They are rhythms, patterns, cycles of destruction and renewal. The quantum sea may be the most mysterious storm of all, but it is also the most creative. It gave rise to us, to thought, to wonder. Perhaps this is the ultimate reflection. The storm is not an enemy, but a mirror. In it, humanity sees its own nature. Temporary, fragile, fleeting, and yet capable of creating meaning, of shaping order, of glimpsing eternity. The search for the quiet storm beneath the quantum sea will continue. Telescopes will probe deeper, colliders will smash harder, detectors will listen longer. Each will sharpen the paradox. Each will illuminate more of the unseen. But the full truth may remain forever beyond reach. The storm may never reveal itself fully, because it is not something to be observed. It is the very fabric of observation itself. Still, the pursuit matters, not because it guarantees certainty, but because it deepens wonder. Science does not banish mystery. It transforms it. It shows that beneath silence lies storm, beneath nothingness lies creation, beneath fragility lies beauty. And so the film closes with silence once more. The sea is calm, the horizon endless, but beneath, the storm still rages, unseen. Every star, every life, every breath is carried upon it. The storm is not separate from us. We are part of it. We are ripples upon its surface. To live is to rise from the storm, for a moment, before returning to it. To exist is to be a wave upon the quantum sea, and to wonder is to glimpse, if only faintly, the storm that trembles forever beneath.